Hi, good day. We are from Team 2 and we are going to present our title named The Law of Thermodynamics Framework for Human Metabolic Processes. My name is Zhi Qing and now I will present our abstract first. This study uses the law of thermodynamics to explain how the human body uses energy from food. We had collected data from 5 people on what they ate and how much they moved over one day. We then calculated their energy balance, which is difference between the energy they took in from food and the energy they used. The first law of thermodynamics shows that energy is never lost but just changed their form. This means that when people ate more than they used, their bodies stored the extra energy, and when they used more than they ate, their bodies burn stored energy. The second law of thermodynamics explains why this process is not perfectly efficient. Even when the body converts food into energy to move or keep warm, some energy is always lost as heat, which is unavoidable. The results show that our findings support these basic thermodynamic principles, but they also highlight that the human body is complex and everyone's metabolism is different based on factors like sex and muscle mass. Now, here is our intro and theory for our title. Our human body operates like a complex engine that constantly converts food into energy to sustain life. This process is known as metabolism, which is governed by the fundamental principles of thermodynamics, the branch of physics that studies how energy moves and changes their form. The human body is considered an open system because it continuously exchanges matter and energy with its environment through eating, breathing, moving, and releasing heat. Two key thermodynamic laws provide a framework for understanding on how our bodies use energy. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed from one form to another form. In practical terms, this means the calories we consume from food must either be used for immediate bodily functions or stored as fat or glycogen or released as heat. The second law of thermodynamics adds an important limitation. Every energy conversion inevitably loses some energy as heat, increasing entropy in the surroundings. This explains why our bodies cannot convert food energy into useful work with 100% efficiency. During cellular respiration, the process that converts nutrient into usable energy, which we know as ATP, a significant portion of energy is always dissipated as heat. Therefore, these thermodynamics principles help us to explain how energy intake relates to energy expenditure through resting metabolism and physical activity, and why energy transformations in living systems are never perfectly efficient. Understanding these concepts is essential for analyzing how the body maintains energy balance, responds to dietary changes, and sustains life through continuous energy exchange with the environment.
So next, I'll be presenting the literature for our study, which focuses on the application of the laws of thermodynamics in the human metabolic system. First, the human body can be considered an open thermodynamic system because it continuously exchanges both energy and matter with its surrounding. We obtain chemical energy by consuming food, while energy leaves the body through physical activities, respiration, and heat loss. This continuous energy exchange allows the body to maintain its normal physiological function. Our first objective is to analyze the relationship between energy input and then energy utilization based on thermodynamic principles. This is explained by the first law of thermodynamics, also known as the law of conservation of energy. The law states that energy cannot be created or destroyed. It can only be converted from one form to another. In the human body, the chemical energy stored in food is transformed through metabolic processes. Part of this energy is used for essential body functions such as maintaining body temperature, supporting organ function, and enabling muscle movement. Some energy is also stored for future use, while the remainder is released as heat. Therefore, the balance between energy intake and energy expenditure follows the first law of thermodynamics. Next, our second objective focuses on the second law of thermodynamics, particularly during cellular respiration and other biochemical reactions. The second law states that every energy transformation increases entropy, meaning that no process is perfectly efficient. During cellular respiration, nutrients such as glucose are broken down to produce ATP, which serves as the primary energy source for cellular activities. However, not all of the chemical energy is converted into ATP. A significant portion is inevitably released as heat to increase the entropy of the surroundings. This explains why metabolic processes are irreversible and why the human body cannot convert all of the consumed energy into useful work. Overall, these thermodynamics principles provide a scientific framework for understanding how the human body converts, utilizes, and dissipates energy during metabolism.
Okay, hello. Now I will be presenting our methodology for our group project. To effectively analyze the relationships between the laws of thermodynamics and human metabolism, our group executed a quantitative study utilizing real-world subject data. For our study design, we utilized a descriptive cross-sectional survey framework. We gathered data from a sample of 5 respondents. The core metrics collected include their age, gender, height, and weight, alongside a 24-hour dietary intake record and a physical activity log. Moving on to data collection, the entire process was executed digitally via Google Form for standardized entry. We focused on tracking two main profiles over a 24-hour windows. First, the dietary log, where respondents record everything they consume, and second, the activity log, where they documented the duration and intensity of their physical tasks. Okay, now how did we process this raw lifestyle data? To quantify the human body as a thermodynamic system, we converted this input into energy unit, which is kilocalories, through two pathways. For energy input, food items were cross-referenced with standard food composition table to calculate total calorie intake. For energy output, physical activities were mapped against standardized metabolic equivalent of task values, factoring in the duration and the respondent's body weight. Okay, now this brings us to our mathematical framework, which consists of 4 sequential steps. First, we calculated the BMR, which is basal metabolic rate, using the Harris-Benedict equation. Next, we derived the active energy expenditure using MET equation. Third, we calculated the total energy expenditure by factoring in the physical activity level and adding a 10% estimation for the thermic effect of food. Finally, we determined the net energy balance by subtracting total energy expenditure from the total energy intake. Lastly, for our data analysis and thermodynamic synthesis, the quantitative metrics were compiled into descriptive statistics, which we visualized using structured table and bar charts. The core of our project lies in how we interpreted this result. We analyzed the net energy balance using the first law of thermodynamics, which is the conservation of energy. A positive or negative balance directly dictates a change in internal energy storage, leading to weight fluctuation. Furthermore, we evaluated metabolic efficiency through the second law of thermodynamics, recognizing that the human body is not 100% efficient, meaning a fraction of this metabolic energy is always dissipated into the environment as heat and entropy.
All right, for result and discussion, we're going to walk through real data from 5 respondents and see these laws in actions. Let's start with the first law, which is energy can't be created or destroyed, only transformed. In your body, that plays out as a simple balance. In figure 1, it's shown that energy intake versus total energy expenditure, the TEE, where the TEE is your basal metabolic rate, or BMR, plus your activity energy expenditure, or AEE. And here's an important nuance before we look at the numbers. BMR isn't one fixed number for everyone. It shifts with sex, age, and body composition. So when we compare people, we're not looking for a normal value, we're looking for how energy moves. From the table shown, 2 of our respondents, R1 and R4, which are both male, were running a significant deficit of negative 663 and negative 608 kilocalories respectively. Their bodies were burning more than they took in, which means they were pulling from stored reserves. R2 was almost balanced, just slightly negative at negative 80 kilocalories, which is barely catabolic. Now, flip to the other side, R3 was in a solid surplus at 528 kilocalories, and R5 was mildly positive at 82 kilocalories. Here's the key point. Under the first law, none of this energy simply vanished or appeared. The deficit respondents converted stored energy into heat and physical work. The surplus respondents conserved that extra energy, most likely storing it as fat. Nothing was created, nothing was destroyed, it just moved. Now bringing in figure 2, if you look at what's actually driving total expenditure, BMR is the heavyweight. It dominates TEE across every single respondent, where activity is almost the supporting actor here. But activity still tells an interesting story. R5 and R3 are both female. Yet R5 activity expenditure was 414 kilocalories compared to R3's just 75. Same sex, wildly different lifestyle or activity levels. And when we look at BMR by sex, our 2 males, R1 and R4, sit at 1,690 and 1,750 kilocalories, while our 3 females range from 1,077 to 1,360 kilocalories. That's not some exception to thermodynamics. That's biology. Lean body mass burns more energy at rest, expressing itself through thermodynamics. When someone is in energy deficit for a while, their body can actually adapt, reducing expenditure by more than you'd predict just from weight loss alone. This is called adaptive thermogenesis, and researchers are still debating how large and how lasting that effect really is. So when we say R1 or R4 were in deficit, that's a snapshot, a moment in time, not proof of some permanent metabolic setting. Now, from the whole body down to the single cell, because this is where the second law of thermodynamics takes over. The second law says every energy transfer increases total entropy, total disorder in the universe. No process is perfectly efficient, and nowhere is that clearer than in cellular respiration. The second law operates at the scale of the cell, where every one of those transformation comes with an unavoidable entropy cost paid in heat, and individual differences like sex, activity level, and body composition don't break either law. They're simply the personal signature of how these universal laws show up in each of us. 2 laws of physics written more than a century before anyone understood metabolism, and they still perfectly describe what's happening in your body right now as you sit here listening to this.